Good. All right, so today we're going to talk about numerical optimization. And this is called numerical optimization. I should say this is really could easily go by the name optimization in general. We're using the term numerical to distinguish from search, which we started before, and which typically deal with discrete quantities. And these typically will deal with continuous quantities that we're optimizing over. I'll cover that in a lot more detail in this lecture, but the general terms that cover this material are also referred to as mathematical optimization, mathematical programming, or just optimization as a whole. Before I start, though, I did want to mention that I think at this point, everyone who is on the wait list or was on the wait list and who had signed up for the Piazza course should be off the wait list now. If you are not in that boat, if you are on the wait list still and signed up for Piazza, tell me immediately, because I think I found all of the people that were in that situation and put them in the course. But if you are not, please tell me. All right, so as Zach mentioned last time, we're taking a little bit of a detour here because just for scheduling reasons, we're going to interrupt search and start search again next week. But this week we'll focus on optimization, in particular optimization over continuous variables. I'll describe what that means, but I think from a bigger picture, this is actually one of the more sort of important new ways of thinking about topics in AI. So just to give an overview, I'll start with an introduction to mathematical programming. We'll talk about some applications of this mathematical programming and optimization. I'll talk about different types of optimization problems, classifying, easy ones to solve, hard ones to solve, different special cases. Then I'll pause for a second and I should get to this part here today, but we'll pause for a second and go over some reviews of linear algebra. Now, linear algebra is not a strict requirement for this course, but this material will use and build upon the notation of linear algebra very heavily. The good news is it's very simple linear algebra. This is really just multiplication. You'll use matrix inverses, but that's about as complex as we'll get here. But we do need to use some of that. And so if you haven't ever seen this before, this could be tricky. We have some extra resources for brushing up on linear algebra or even learning it anew if you haven't seen it before. So if you're in that boat, send us an email, come talk with us. I put some up on the website. I think I might put some more up later as well. But we will use this, and you'll see today about the extent of what we'll use. Then we'll talk about convex optimization problems, which are a very important subcategory of optimization problems, which is really going to take most of this lecture, actually. We're going to spend most of the time on convex problems, really because the difference between convex and non-convex often distinguishes between things we can solve efficiently or in polynomial time and things we cannot solve efficiently or things you need exponential worst-case time algorithms to solve. Now, search oftentimes is actually always in this, or very often is in this category here. So we certainly will spend some time on that. But in this unit, at least, we're going to focus largely on the convex setting. And finally, I'll talk, and we won't get to all this today. This is today and tomorrow, and even the slides aren't quite all up yet. But we'll also talk about ways to actually go ahead and solve these problems, both from a conceptual standpoint and what are the algorithms people use to solve them, and from a practical standpoint in terms of how can you actually solve, using Python, some fairly complex optimization problems. So let's just jump right in and talk about mathematical optimization or mathematical programming. I'll clarify the difference between those two terms in a second, but I'm going to use them interchangeably on purpose because you will see both of those in the literature. So, as I said, this is one of the primary sort of themes of AI research within the past, I would say, 15 years. Going back 15 years, you didn't see a lot of optimization mentioned in AI conferences, and now it's really all over the place. There are papers that are just on techniques for optimizing a certain function quickly. These become papers in AI now. So this is a very, very popular topic and really growing in popularity, both in AI and in subfields like machine learning and other areas. And importantly, because the textbook kind of came out before this really became a main wave and kind of delineated its topics before this came out, this topic is not highlighted that much in the textbook, at least not in the way that we really present it here. So all the reading for this unit here is going to be on supplementary material. There are a few extra materials on the website. These are actually write-ups that I had developed for other courses, but which are very applicable here. There's one on linear algebra and one on convex optimization, which cover most of the material that we'll actually present here. So I guess from a big standpoint and kind of situating this within AI, there are a lot, I described before why a lot of AI problems can be phrased as optimization problems, right? We talked about search can be phrased as optimization, finding an optimal path subject to certain constraints. That was kind of how we described a lot of these problems. But there's a big distinction here between what I'm calling search problems, which is sort of what we talked about last time, essentially finding a set of discrete points or a discrete plan through a graph as a way to kind of capture a lot of search. And now what I'm calling mathematical programs. And it's really kind of a very interesting situation here, because in search, we typically are optimizing over discrete variables, right? So we have to pick a path through a graph. We have to pick our variable is what's the second node in our path, right? Those are our variables. What are the nodes in our path? Those can't be 0.5 of node 1 and 0.5 of node 2. That's not how graph search works. You have to pick a single node that you're going to. So it's discrete, and therefore the number of possible solutions you have is finite. Now it's potentially very big, but it's still finite, right? Because you could just potentially at least enumerate all possible solutions, and you're sort of okay. Just pick the best one, then you're done. Yet the difficulty of solving these, in the worst case, the time complexity at least, is exponential, right? We saw that in these search algorithms that we mentioned last time. The time complexity is oftentimes looks like b to the d or something like this, where d is the depth of the search tree and b is the branching factor, or some term like that, it looks like. So discrete, finite, exponential time. Now, what's amazing about mathematical programs is that we move from the discrete space to the continuous space. So instead of saying we have to pick either node 1 or node 2 as our solution, we say, well, we can pick some variables that are sort of continuous valued, say, half of this one and half of that one, or anywhere in between. Right? Now we've gone from a number of possible solutions from being finite to being infinite, because we're optimizing over continuous variables here. Yet, for a very large class of problems, in particular problems that are characterized by convex optimization, we can often find polynomial time solutions. So we actually can very efficiently solve very, very big problems. And this is actually a pretty mature technology in that there is code, both in that the algorithms are very well worked out and in that there is code you can download to solve these kinds of problems. So let me start by just sort of giving the basics of what a mathematical program is, or an optimization problem. Again, I'll use both those terms interchangeably here. So our problem here is we want to minimize over x this function f of x, okay? Subject to the constraint that gi of x is less than or equal to 0 for a bunch of different i's. Okay? Here, x in Rn, and I'm going to use this a lot, but I should sort of mention, because I don't define this until later, but this notation here means x is an n-dimensional vector. Okay? That means it's a quantity like this. It's a vector, and in fact, it's a column vector that has x1, x2, all the way to xn as its entries. Okay? That's what that means here. This is the optimization variable. That's what we are going to choose. We're going to choose the variable x that minimizes this function, and you'll see some examples in a second that kind of hopefully clarify this, subject to these constraints. All right, so f here, and again, just to sort of mirror what I have there, f, which is a function from Rn to R. That's what this means here. This means f takes as inputs vectors in Rn and outputs a real scalar number. This is the objective function. This is the function that we want to minimize. And by the way, I'm sort of a little bit of a stickler here for saying, not always in sort of when I'm talking informally, but in class at least, I'll try to be a stickler about saying minimize rather than saying min, because min is a mathematical operation, right? It's the minimum element of some set. Here, this is describing a procedure that you want to do. So we want to minimize, find the minimum value of all possible x's of this function f of x subject to these constraints here. These constraints functions are also functions that map from Rn to R. And in this case, they would be called inequality constraints, meaning that the x we find has to satisfy this constraint that these functions are all less than 0. Now, of course, this is very abstract here. I'll talk about what I mean by this in much more detail shortly, both today and tomorrow. But this is the overall kind of generic formulation you see. And a couple of definitions here. One thing we'll talk a lot about is the feasible region. So there are two real kind of functions here. One are constraint functions, and one is an objective function. Well, there's lots of constraints and one objective. The feasible region is the set of all x that satisfies the inequality constraints. It satisfies the constraints of this optimization problem. Okay, and so there are potentially lots of these that satisfy this. There also, by the way, could be none, in which case this optimization problem as a whole is infeasible. But there could be a lot that satisfy these constraints here. And of those that satisfy the constraints, we just want to pick the best one here, the one that minimizes this function, subject to the fact that it has to obey all the constraints. And finally, what we say is that we say that x star, and we put a little star on it, is an optimal solution if, first of all, it's in the feasible set. So it has to obey those constraints. And then it's the objective of x star is less than or equal to the objective evaluated at x for all other x's in the feasible set. So kind of what you expect, right? One important point here is that x star is an optimal point. There can be more than one, certainly. There can be multiple optimal points here. That's why we have a less than or equal to here, because there could be other x's that achieve just as good objective value, and those would also be, therefore, optimal solutions. But this, if we get it, it is an optimal solution. Yes, question? Yeah. Yeah, so this is a bunch of functions that we just say those have to be less than or equal to 0 in order for it to be feasible. Right? So this could be for any function you want to define here. We'll map inputs to real values. And I'm saying the set of feasible things there is a set where those are all less than 0. You could make that less than anything you wanted to. And we'll see some examples in a second that might clarify things a little bit. But essentially, these constrain the set of allowable solutions. So maybe you want your first variable here to be less than 5, say. You write a function that's just the first value there, minus 5. It has to be less than 0. You want it to be greater than 5. You say negative, the first thing, is greater than negative 5, or less than negative 5, plus 5 less than this. So this is a very kind of general way of cataloging a bunch of possible constraints on your inputs. Because these are very generic, kind of general functions here. They can be whatever you want. For now. We'll put constraints on them soon. Yeah?
Is a problem where you have equality constraints, is that distinct from classification programs?
Yeah, so I'm essentially in the general case, you can have equality constraints by just saying that having one of your g's be a function and having less than or equal to 0 and having negative g be also less than or equal to 0, then it has to be equal to 0. In practice, what's it doing here? In practice, we typically treat those differently. Coming up? No? Maybe? Okay. In practice, we treat them differently because they actually, the algorithms that work for one don't necessarily work for the other. And in fact, when I talk about convex programming in particular, we will talk about having explicit equality constraints. But for now, you can enumerate whatever you want in this sort of very generic kind of framework here. Who here has seen optimization like this before, by a show of hands? Okay, most people, okay. But not everyone, so that's fine. Okay, so first, a little note on naming here. So I'm going to call a mathematical program or an optimization problem, mathematical optimization problem, etc. That will refer to this problem here exactly. A problem of this form. So a mathematical program is a program like this. Using program kind of oddly here. This is the kind of the term program that's used in math. Or just an optimization problem is this thing. Now, the field of numerical optimization or mathematical optimization or just optimization, that refers to the general kind of study of these problems, as well, in particular, numerical optimization refers to the study of how you solve them on a computer. So that's just a little terminology to keep in mind there. It's not a big distinction that's very important here, but just to keep in mind, I'm going to, as I said, use these kind of interchangeably here, and so it's useful to have these different things in mind. All right, so let's talk about, now that sounds kind of abstract so far, so let's just talk about a few examples of problems in this form that we might want to solve for some reason or another doing AI research. Let's start with the first one, which is kind of one of the classical optimization problems. I think this is one of the first ones that was ever solved, and it's solved easily because it actually has, in this case, a closed form. That we won't worry about that for now. The idea here is that we have a bunch of points. Okay, and think of them for now, just these points are in 2D space here. And I'm labeling the axes here as A and B. You might see these as usually X and Y here, but I'm going to always use X as our optimization variable. So I don't want to be confusing about what's optimization variable and what's the points here. The points are going to be X and B. So the X-axis you can think of as, sorry, they're going to be A and B. So the X-axis here, the effective X-axis is the A-axis, and this is the B-axis. We have a bunch of these points. So the points are labeled essentially AI and BI. Okay, we have a bunch of them. We want to find a function h of A such that h of AI, and I'll write it kind of informally at first. We want h of AI, we have m of these. We want h of AI to be approximately equal to BI. As measured in this case by the difference between these two things squared. Okay, this is a very common problem called a least squares problem. This is least squares just in really one input dimension, so it's a very simple least squares problem. And the picture to have in mind here is just essentially trying to draw a line through these points that minimizes the sum of these squared errors. Okay, so we want to minimize over x. Here, oh, I should also add, the form of h, A equals x1 times A plus x2. Okay, so x1 in this case, the first element of x here is going to be a two-dimensional vector that we're optimizing over. x1 is essentially the slope of this line, and x2 is the intercept. Okay, so if A is equal to 0, you just have x2, and otherwise you scale this function here. You scale A by x1, and you add that to x2, right? So you've probably seen this. This can be kind of confusing because you've probably seen it in the other way around, where it's written ax plus b equals y. But here again, I'm trying to keep the notation that x is the thing we're optimizing over, and so I'm saying that a and b are what's given to us, and x is what we want to find that minimizes this function here. Okay. This now is an example of in this case, unconstrained, but an optimization problem. Right? How do we find the x here that minimizes this? Well, we want to search over all possible x in some sense, right? That's an infinite number of possible x's. X is continuous. In this case, x is going to be a vector in R2. We want to search over all of them and find the best one. Let's take another example. This is called a Weber point, or a linear facility placement problem sometimes. It goes by a bunch of other names as well. And it's a deceptively complex problem. Not that complex, but it's harder than you would think. It's a really simple idea. Okay, we have a bunch of points. Again, a bunch of points AI and BI in 2D space. I should have left that. Okay, a bunch of points in 2D space. And we want to find a point x1, x2 that minimizes the sum of the Euclidean distances to all those points. Okay? This is harder than it looks. At least you can't, not that much harder, but it seems so simple. Like there should just be an expression for writing down what x1 and x2 are, but there really isn't. So it's a sort of, has anyone seen this before, this problem like this, by the way? So for a simpler case now, what if the points were in actually one-dimensional space? What if we just have a line here? Okay, now we just have A's, so this is A1, A2, AM. In that case, what would the Weber point be? Well, I heard a bunch of different things there. I heard average. What else did I hear? The mean. Okay, same as the average. What else? Other things? Everyone says mean. Any other guesses? I heard it there. It's the median. It's not the mean of these points. Okay? And the way to see that is very simple, right? Suppose you just have all the points here. Okay? All of them are overlaid here. If you move anywhere this way, it'll increase the distance, this distance, and this becomes your sort of point x. You have one over here. The mean will always be a little off from these guys. But if you move this way at all, then you pay a cost, whatever you moved over, called as d, you pay that cost, m minus 1 times, and you only gain a little fraction there for that one thing you did better on. What the mean actually minimizes is the sum of the squared differences, or sum of the squared distances here. So if we didn't have this square root here, the solution there actually would just be the average of all the points. You take them and you just take their average, and that becomes your solution. Here, in the 1D case, it's simple. It's the median. Okay? Here, there's no real way to solve it, strangely enough. I mean, there is, but you have to solve it as an optimization problem, really. So what you'll do at the end of this lecture, or 2 lectures, you should be able to write a 5-line Python script that will solve this. Okay? This is actually pretty, I just found this very interesting the first time I saw this, right? Because it seemed like there should be a very simple solution, yet there isn't. And the only, or the easiest way to solve this, at least as far as I can tell, is to think of this as an optimization problem. We are minimizing over x this thing. This winds up being, as I say, one of the problems we can solve easily. And just solve it as you would solve any other problem like that, using whatever libraries you need externally to do it. It's actually very hard to solve, because it ends up being even a complex optimization problem that I probably couldn't write the algorithm off the top of my head that would solve that, but it's definitely doable if you use libraries that already exist. And you can also, of course, constrain things a little bit. So now say that I want to do this optimization here, but also keep x within a certain range. And I should say, there's a ton of applications you can come up for these things, right? So imagine, we talked a lot about things like scheduling yesterday, or last lecture, and routing of packages and stuff like that. Well, this is actually a really important problem in that space, right? Because if you have a bunch of destinations you want to get things to, and you want to minimize the say, travel time, which is maybe proportional to distance to all of them, then you want to pick the point as your, say, hub to ship packages or whatever, that's the closest to all of them. So, interesting problem for a lot of practical reasons as well. We can solve constrained versions too, and that is where we start introducing things like those g functions here. So for example, the constraint that x1 be greater than or equal to some lower bound al. All right? The way you encode that is you would say that my function gi is going to be of x is going to be equal to al minus x1. And that thing has to be less than or equal to 0. And that's the same as its constraint here. And you can do the same thing for the other side too. It just ends up being a negative sign on this one. I guess, and a positive on this one. Okay. So you essentially do the things in the same way to encode these constraints. And that would be sort of the situation where you had some constraints on where you could place your facility, and you couldn't move outside some box or something like that. By the way, if you have this constraint, that x1, say, has to be less than or equal to some lower bound AL, and x1 has to be x1 has to be greater than or equal to some bound AU. So basically, you have your line here, and it has to fall in this range. That problem now becomes, in the worst case, NP hard to solve. So little changes can make these things a very big difference. Make a very big difference. If you constrain yourself to lie within this region here, you can solve it efficiently. If you're lying outside the regions, not efficient anymore. And we'll get to that in a second when we talk about convexity and the properties of convex functions. Now, many, many more applications, I should say. This is just two very quick ones. But really, there is as evidenced by the amount of publications and just interest in this area, there is a wealth of applications in things like scheduling and operations research, but also things like engineering, control, machine learning. These things all really fundamentally use tools from optimization. All right, so let's talk about classification of problems now. The big thing that I'm going to try to get across in this lecture is that there are two very kind of important distinctions when we talk about optimization problems. And it used to be that there were other ones. So if you've taken old courses, you may have heard things like linear programs or linear programming versus nonlinear programming. This was an old distinction people really use to talk about linear programs, which were a subclass of problems that are easy to solve, versus nonlinear programs, which is everything else that were hard to solve. Well, I think it's become pretty clear that's not the right distinction. The right distinction is between what are called convex problems and non-convex problems. So you can divide up the space of all optimization problems in one of these two categories. And in general, these ones here are easy to solve. When I say easy, I mean there are polynomial time algorithms that will give you solutions to numerical precision. That's what I mean when I say easy. And what I also mean, by the way, is we can actually solve a lot of them when we code stuff up pretty quickly. These ones here typically are not of that category. There are some very small subsets of problems here that you can still solve efficiently, but they're few and far between. For the most part, if you're in the non-convex regime, and I will define what those mean in a second, by the way. If you have not heard those terms before, don't worry. For the most part, these ones are very hard to solve. Now, within convex problems, you have a bunch of categories that you may have heard of or may have not. If you haven't, don't worry about it. These are different subtypes of problems here that are very popular because you can express them in a standard form. And so a lot of kind of off-the-shelf libraries address one of these classes of problems. But they include things like semi-definite programming, quadratic programming, or linear programming. And on the other hand, non-convex side, there's a bunch of things. The one that we'll talk about, well, I guess we'll talk about a lot of them because a lot of search problems are fundamentally non-convex optimization problems. But the one that we'll talk about really in this context here are something called integer programs. We'll talk about how you solve integer programs. And it ends up being this really cool combination, essentially, of exactly the kind of search algorithms we're using, combined in the last lecture, but even more in future lectures, combined with methods for linear programming and convex optimization. So it's this really cool merging of the two. Unfortunately, it is exponential time, like most searches, but it's a very cool subgroup of non-convex problems that, even though they are, in the worst case, very hard to solve, there still has been a lot of progress on solving these things better in recent years. So that's kind of the overall landscape here of optimization problems, at least as we'll look at them in this course. Now, I'm going to spend most of the rest of the time in these two lectures talking about this half of things. We'll have a separate lecture on integer programming. That's coming up later after we've covered search. And I'll mention it a little bit in terms of, largely in terms of ways in which you can solve these things either approximately say locally, which can be still fast but are suboptimal, possibly, and solving them globally, which in general is kind of exponential time complexity and kind of hard to do. So most of the time here, but a little bit of time discussing this, not today, but in the next lecture. So before I move on now, let me get to the dreaded review of linear algebra. As you probably already saw already, I'm using some linear algebra notation. And so it's important to just know what I mean by all these things. Again, this is easy linear algebra. It is literally, probably the first couple weeks of linear algebra course. We're talking about inverses here, but we're not talking about things like eigenvalues or eigenvectors or these more complex topics, or even things like rank and range and null spaces. They're very important, and they're great to know, and you should take a linear algebra course, but they're not really required for this course. We'll try to keep them out as much as possible. So hopefully this is a review for everyone, as I said. If it's not a review, don't worry. You can probably learn simultaneously everything you need to know about linear algebra for this course. But let's just go through it really fast here to review for people that haven't seen, say, this notation before with the little, R's and I don't have it here, but the R's with 2 lines and everything like that. OK, so starting off, vectors. We say that x is a vector in Rn. We write it like this. X is in Rn. Rn, and this sort of, I don't know what actually that's called. BB is what I always type when I type it. I forget what that script is called. Anyway, that script R, and I'm going to write it like this. I can't quite be as fancy with all the double scripts there, but I'll write it like that. That is the space of all n-dimensional vectors. So saying x is an Rn means x is an n-dimensional vector. That also, by the way, means that x is a vector with n rows, or rather a matrix with n rows and 1 column. Vectors are always column vectors in our notation here. A matrix, and again, this R means it has real value entries. You can have complex value entries. You can have other sets of entries as well, but we're going to mostly focus with real valued entries here. I think only focus on real value entries in this course at least. We're going to write this saying A in R to the m by n, meaning that A is a matrix now. If I write this, that means A is a matrix with m rows and n columns. If we want to talk about a specific entry, we'll write x sub I, that will be the ith entry, or A sub ij, that will be the entry in the ith row in the jth column. So here, this would be aij, this would be the jth column and the ith row. Sometimes we will actually call a whole vector, use a whole vector that has a subscript. So we'll write something like this. We'll write something, it's kind of gross, like this, saying AI is in Rn. Now we've kind of screwed everything up because now we can't use a subscript again, but we might want to do this anyway. So if we do this, we'll usually write something like this to denote the jth entry of a vector, which itself is indexed by some number. You're going to have to get used to a little bit of ambiguity here in notation. It's just life. That is what you will see in literature, so you have to get used to it. One operator that's very important is the transpose. The transpose switches the rows and columns effectively of a matrix. So the ij element is equal to the ji element of its transpose. That also means that if we want to talk about a row vector, a vector with 1 row and many columns, we would say something like x transpose equals this row vector, right? Because we've transposed the column vector to be a row vector. All right, addition. Addition's easy. You have 2 matrices. They have to be the same size. Their sum is just the adding up corresponding elements in each matrix. Subtraction is the same thing. Multiplication is a little bit trickier. Multiplication, which you've probably hopefully seen this before, but multiplication is defined in the following way. You have 2 matrices, A in n by n, A which is an m rows n columns, B n rows p columns, then A times B the ij element of that equals the sum from k equals 1 to n of aik plus times bkj. Okay, that's just what's written here. Very important, though. Multiplication is only defined when the sizes of the matrices are correct. And again, I'm going to say this, and you're all going to nod your heads and say, yes, of course, of course. I guarantee you people will write homework assignments in this class where they do not obey these rules. And so don't do that. If you write a times b, the way to remember this, right, is that if you write out the size of the matrices on top of them or below them or whatever, the inner dimensions there have to be the same. And the dimension of this product is equal to the outer dimension. So this whole thing here is m by p. And that falls out just from this definition here. Okay? Now, a few properties. Multiplication of matrices is associative. That means we can do b times c or a times b first. Doesn't matter. So we'll typically just write it a, b, c. By the way, that does not mean those are the same complexity for those things. This can be many more computational steps to do it one way versus the other way. Just know that. We're not going to worry too much about that. But know it can matter from a computational perspective which thing you do. It's distributive. So a times b plus c equals a times b plus a times c. Importantly, it is not commutative. Matrix multiplication is not commutative. A times b does not equal b times a. This is true for many reasons. First of all, the sizes here might not even make up a valid matrix product, right? These can be a valid product. This could have n columns, and this could have n rows, whereas these other dimensions don't match. So you can't even write this. Even when you can write this all, say these are all n by n matrices, this equality will not hold here, except in very special cases, which are not common. You're not going to run into them that often. And finally, if you take the product and transpose it, that equals the product of the transposes. What's happening there? It's closing the blinds for some reason. That equals the product of the transposes, but you have to flip the order, right? So a times b transpose equals b transpose times a transpose. Again, that follows directly just working out the math from this thing here. All right, one very common product, which is so common that we'll see it a lot, is an inner product of two vectors. So we have two vectors, x and y. They're both vectors in Rn. Then the quantity x transpose y, which is also sometimes written like this, little brackets around x comma y, that is just equal to the sum from I equals 1 to n of the corresponding elements xi and yi. So you multiply corresponding elements together, add them all up. That follows exactly from the definition of matrix multiplication. If you just look at the definition, treat those as matrices, this was exactly what it is equal to, but it's so common that you will just point it out specifically. You'll see that form a lot. The identity. The identity is a square matrix that has ones on the diagonal and zeros everywhere else. And it has this nice property that the identity times a matrix A is just equal to A, which also, by the way, equals A times the identity. But importantly, these two matrices here are different size, or can be different size identities. This one can be, if A is m by n, this one would be m by m, and this one would be n by n. Okay? Usually you don't write the size below it. You may see that sometimes, people writing like A, I, N, something like that. Usually it's implied by the size of the other matrices, so you don't have to bother writing it. Finally, the inverse of a square matrix. Importantly, A here is square. All right, A inverse is the unique matrix such that A times A inverse equals the identity, which also, by the way, equals A inverse times A. You can do it on both sides. It does not have to exist. For a random matrix, say, if you make a matrix with random Gaussian elements, something like that, it will exist with probability 1. But it doesn't have to exist. Very importantly, only for square matrices. Do not, this is another thing you see, do not invert a non-square matrix. I guarantee someone will do that on the homework. Please do not do it. Finally, when you have a product, A times B, all inverse, this equals B inverse times A inverse, very importantly, again, only when both A and B are invertible themselves. So you could write this thing here in cases where A and B are themselves not square, in which case you cannot do this. Right? When A and B are square, though, and they're both invertible, this equality holds. All right, so I went through that very fast because I think a lot of people were sort of nodding along and getting it, but let's make sure everyone's got it. So here, again, and I'm doing this because everyone knows this, yet somehow everyone, ooh, I got like really weird. See, if I publish the poll, will that, oh man, it like reverted back to the LaTeX for some reason. Let's just try to see if it renders it better. Do it again. Okay. It's open now, right? Okay. So these matrices here, A is M by N, B is N by N invertible, X is an Rn, Y is an Rn. Which of these are valid expressions? These are expressions that you could write on a homework assignment and not get points off for them. That's what I mean by valid. What I really mean by valid is two things. If there is an equality here, that means the expression is actually true. But more importantly, can you even write that? Does this even compute some of these things? Does it have any meaning syntactically? Because a lot of them don't, and yet you still see a lot of these on homework. So we'll go through all of these. Check the ones that are valid linear algebra statements, and don't check the ones that are invalid statements. All right, we'll give it maybe till 15. 2:15. Can everyone read these okay? Because they're kind of hard to read the math, but you should be able to hopefully get it on your phones or computers a little bit better. The phone showing the LaTeX? You can read these though, okay, here? Okay. I can zoom in or something too if it's helpful, but okay. Let me see if I know how to do that. This is, I might not be able to do that actually. I can't do that. If you can't see, just ask me for clarification on one of them. I can't actually zoom. I will do it for next lecture. I'll make this so it zooms a little bit more by default. But for now, we'll have to go with as it is. No votes yet. Don't worry about taking too much time with these things. Just sort of check it's okay if you get a couple wrong. Again, the most important thing is actually just do these questions, submit an answer. That's more important than getting the right answer necessarily. Yeah. Yeah. Yes. You can solve it with convex optimization, absolutely. That's how you would solve it typically, or some approximation to those methods. Yeah. You can under certain things you can do it that way, but yes, I mean I would actually even say the geometric median is defined in that respect. So that's how I would characterize the geometric median, rather than saying it's just the geometric median. That's sort of content free, right? It's the same thing. Yes. All right, 22 votes so far. 2:15 is approaching. It's come, it's here, but I'll give people more time still. I think this maybe takes a little bit of time sometimes. All right, we're gonna give 10 more seconds. If you haven't gotten them all, just submit, because otherwise you get no credit. All right, everyone good? Actually, does anyone need more time? I don't want to be too cruel about this kind of stuff, so. Everyone's good? Okay. 50 votes in. All right, close the poll. Ready? Okay. Done. Sorry. Still loading is what was happening? Oh. Okay, all right. Okay, let's see what people said. Okay, this one, yep, correct. Everyone got that. Those dimensions all add up correctly, everything's good. This one here, definitely not. You cannot add A and B together. They are different sizes. Remember, we assumed that M was not equal to M here. So these are different size matrices. You cannot add them together. This one here, also correct. A times B inverse. B is a square invertible matrix. This is the identity. A times identity just equals A. Works well. This one here, absolutely not. I never want to see this anymore ever again. There's an A inverse here. Okay, A is not a square matrix. Please do not write A inverse if A is not square. It does not compute. I mean, it doesn't make any sense. There are analogs of inverses that do apply to non-square matrices. Don't try to weasel out that way. You're not using the pseudo-inverse here. It's just an inverse. Don't write this. Okay, moving on. This one, also no. X here is a vector. So X would be an n by 1 vector. So this term here, X times B, X would be n by 1. B is n by n. N and 1 are not the same, so the inner dimensions there don't add up. Doesn't work. Same with x squared. X squared, by the way, means x times x. Right? That's what x squared means. Again, it doesn't make sense. Right? This is n by 1. This is n by 1. You can't multiply them together. I don't know what people mean when they say that, really, right? Because it can mean a bunch of things, and it's not clear what it does mean. This one is true. X transpose Y equals Y transpose X. That's because this thing here is just the product of corresponding elements all added together. And as you can imagine, it doesn't matter which order you do these in. It is the same thing. Right? This here is not true because, unlike this one, these can actually be different sizes. So A times B, that is going to be M by, in this case, M by N. This is going to be N by M. These are different size matrices. They could not, and that therefore definitely not ever be equal. And here, again, people committed that horrible, horrible mistake of inverting a non-square matrix. So I'm saying this all a little bit. Don't worry if you got some of these wrong. It's again, linear algebra was not a prerequisite for this course. This is the extent of linear algebra you will need for this course, I think. We will try to make it that. There will be some calculus too, but this is, in terms of linear algebra, this is sort of the extent that you actually need. And so if you got some of these wrong, take that as an opportunity to say, okay, I should brush up on my linear algebra. There's a set of notes on the website. Go through those. I'll also point out to a set of online lectures I developed on linear algebra. You can go through those as well. Just sort of go through them and get these to the point where you're comfortable with all of these expressions and can answer them all correctly. Okay. Any questions about this? All right. Ooh, I think I did a horrible mistake there. Hang on one second. This is going to, whenever I scroll these things, it really ruins everything. I tried to zoom in. That really messed me up there. OK, now let's talk about convex optimization problems. And we'll go through this in a few steps. This is going to be actually the majority of this lecture and the next one, so we'll spend some time here. OK, so I'm switching now from this set of optimization problems, which are clearly very useful, right? Clearly, those are very, very powerful. You can really optimize whatever you want. You can say, I want to optimize, you can encode any NP hard problem that way, because I can just say, I want to optimize the length of my traveling salesman path or something like this. OK, so why are we making the switch to convex methods? And I highlighted this a little bit before, but convex optimization problems are a very limited, but also very powerful subset of optimization problems as a whole. All right, so what makes them very nice, and we'll prove this in a second, is that roughly speaking, they allow for, well, we won't prove this. We'll prove why this, we'll prove a property that is important for this, I should say. Roughly speaking, these problems allow for efficient, and by that I mean polynomial time, solution methods. Meaning that we can actually solve very big problems if they are convex problems. There's also a beautiful theory behind convex optimization. Things like duality and all these kind of wonderful bits of theory come out of this. We're not going to worry about that at all in this course. So sorry, if you love theory, still might like this course, but we're not covering that element in this course. So can solve them efficiently is a beautiful theory, but the real important point, of course, without this, there wouldn't be much interest, is that there are a ton of applications. There really are a ton of problems that can be solved in this framework here. And in particular, for example, those two we showed previously, the Weber point problem and the least squares problem, those are both examples of convex problems that we might want to solve. And there are a lot more. And this has been kind of the realization over the past, say, 20 years in AI has been that we can formulate a lot of problems like this and solve them really well. And at this point, I would go so far to say is this is a mature technology, meaning you can download code, and we will download code, in our case in Python, where you input problems in a very generic way, and it solves them. And you will solve what seemed to be, and I think what at least, say, 20 years ago, would have been considered very complex problems to solve. You can just type them in and solve them in, for medium-sized problems in a couple seconds. All right, so let me define this formally, what a convex problem is. I'll define it kind of in a little bit of an abstract way at first, and then get a little bit more concrete, and finally talk about some nice properties of these things that really make them useful. I don't think we're going to get through all this today, so I think we'll be sort of stop in the middle of all this discussion here, pick up next time, and then also talk about non-convex methods, and more importantly, probably about methods for actually solving these problems. So, a convex optimization problem is a specialization of a mathematical programming problem of the following form. Minimize over x, f of x, that's our objective from before. I'm going to write our constraints now, just rather than saying some function is less than some other function. We'll come back to that in a second, or some function is less than 0, rather. We'll come back to that in a second, but for now I'll just say x has to lie in some set C. So we're going to minimize this subject to the fact that x lies in some set C, some feasible set here, where importantly, what makes this a convex problem are two things. The function, the objective, has to be what's called a convex function, and the set, the feasible set here, has to be what's called a convex set. So I've really just shifted words here, right? I haven't actually defined anything. What we're going to do now is I'm going to go ahead and define what I mean by convex functions and convex sets. Actually, in the other order, though. I'm first going to define a convex set, then define convex functions. A little bit simpler that way. And then that will, in total, categorize what I mean by these things. All right. We'll start with convex sets. A convex set is a set C such that if you take any two elements in C and take what's called a convex combination of these elements. What I mean by that is we take x and y, they're both in C, and we're going to take some real number theta, where theta is less than or equal to 0, sorry, greater than or equal to 0 and less than or equal to 1. It's a real number. And we form the combination of these two things, kind of a weighted combination of x and y, where we take theta of x and 1 minus theta of y. What this is that this defines the line between x and y. So this is x and this is y. By taking different values of theta, we can sweep out the line between these 2 points. But it's just a line, right? It does not go beyond the points. We don't include this element over here. We're just talking about the line between x and y. And the fact that it has to be between it comes from the fact that theta here has to be between 0 and 1. Right? So if theta is 0, we have the point y. And if theta is 1, we have the point x. And if it's 0.5, we have the point in the middle, etc. Okay, so this, by varying theta, we sweep out all the points in this line here. Now, a convex set is a point where this whole line also lies within C. So this is the set C. We take any 2 points, the line between them also lies within that set. Okay? A non-convex set then is everything else. It's a set where you can form some line, and that should just be one line. As long as you can take a single line, form the line between 2 points, and if that line does not lie within that set is not a convex set. And now the way that you actually sort of get an intuition for these things is more through some examples. So for example, let's take a few instances of convex sets. Well, first of all of Rn is a convex set. Right? These things can be unbounded. They can be open sets. That's fine. Obviously, if x and y are in Rn, then this combination is also in Rn. Fine. Not very exciting here, but it is an important convex set. Intervals are also convex sets. So if we have some x in Rn, and we have the set where x is greater than or equal to some lower bound, some set of lower bounds L, and by this I mean actually element-wise equality. So x has to be greater than or equal to all the corresponding elements of L. So basically, if you take L a vector here, and x is a vector, this has to be less than this, has to be less than this, etc. The corresponding elements have to be less than the corresponding element. And same for an upper bound here. This is a convex set. And the way to think about this is kind of like this is sort of defining a sort of hyperrectangle, right? So in 2D, this would be essentially defining some rectangular region. This point here would be L1, L2. This point here would be U1, U2. And the region, the convex region, would be the region, the rectangle defined by these points here, because any point, x, any other point, y, you take their line, it'll lie within that rectangle. A little bit more generically, you can actually say that any set of linear equalities. What I mean by that is, if we have some matrix A, which is M by N, and we have matrix B, or vector B, in Rm, then the set of all x such that Ax, this is now, remember, a vector in Rm, the set of all Ax being less than or equal to B, that is a convex set as well. And here, this isn't maybe immediately obvious, but it's very easy to prove. Okay, and the proof is very simple. If they're both in C, it means that a times x less than b and a times y is less than b. That also means, by the way, that we can just multiply them by theta on both sides of these things, and 1 by theta on both sides. We add these two up then, and we get that theta times, remember theta is positive, so the signs are all okay here. And it's positive and less than 1, so these things here are both positive, so we can do all this. Or at least they're both non-negative, I should say. We add them up, and then this whole sum here is less than or equal to b. We just distribute the addition and multiplication here, and we get a times this quantity is less than or equal to b, and that just means that theta times x plus 1 minus theta times y is in C. So you can look at the notes yourself and kind of go through that derivation if it was a little fast there. I'm mainly just putting it to have in the notes. It's very, very simple, but it's just this is how you actually show that these sets are in fact convex, usually by just going through the derivation and seeing that it is in fact the case. That's at least one way you can actually show it. The same thing holds for linear equalities. Linear equalities. So if this holds with equality, that also is a convex set. And finally, a very useful property, which is essentially usually the other way you show something is convex, or a set is convex, is that if you can represent the set as an intersection of other convex sets, that is also convex. This one's also pretty easy to prove. Essentially, if it's in the intersection, it's in each of them. So a linear combination, or the convex combination is in each of them. So therefore, the convex combination is in the intersection. That actually is written up in the notes if that was too brief of a little digression there. But just take it so that these things are all rules on how you express, or rules for constructing convex sets. So now let's go over some more examples here, and I'll talk about which of these are in fact convex sets. Okay, so I'll go through them. Again, I'm sorry that the size is not great here. As I said, in the future I'll try to get a better zoom or something on these equations. It's just a LaTeX. Everything else is pretty readable, but somehow the LaTeX is not that easy to read. So what we have here is we have x and R2, x1 is greater than 0, and x2 is in this range. Is that a convex set or not? x1 plus x2 minus x3 equals 1. Is that a convex set or is it not? The little caret here means or. So actually, wait, this one is, I didn't define this. OK, I think this left out something here. Here, I think C1 and C2 are arbitrary convex. Well, sorry, I shouldn't say I think. Here, in this one here, C1 and C2 are arbitrary convex sets. And I'm asking you, is the set of all x such that x is in C1 or x is in C2, is that a convex set? And here I'm asking you for specific x1 or C1, and that should be C2. For C1 and C2 here, given by these things, is the set of all x such that x is in C1 or x is in C2, is that a convex set? So let's see what people, oops, it's not published yet. Man, hide results and publish, OK. And now they, of course, make it incredibly hard to read. I do that. That must be a bug in Piazza, right? That it sometimes just decides to show you no LaTeX. OK, so we'll take till about maybe 38 or so, 5 minutes. Any questions here? This notation is getting a little bit cumbersome, but I want to make sure everyone understands what all of these sets are defining, at least. Then you can decide if they're convex or not. But are people that okay? Are the phones working out kind of worse than I thought? Or do you really need a computer to do this well? It's the first time. What, the phones are okay? Okay. Maybe if I make the text bigger here too, it'll be a little better for the phones then, even if it shows the LaTeX alone. Yeah, I guess you're out. So I guess look at this, because some of these ones like this, especially, this will be really hard to read on a phone if you're just reading the raw LaTeX. Do you have the app or are you using the website on the phone? Actually. Okay, so using the website, that's actually too bad. The website apparently works on your phone, but the app does not work. That's a shame. What was that? It uses LaTeX for you? Okay, yeah. So the app apparently doesn't show LaTeX, but the website shows LaTeX, it sounds like. Oh, okay. So maybe it works on iPhones, but not on Android. Wonderful.
Last option, the second one is C2. Right?
This should be C2 here, yes. Sorry about that. This should be C1 equals this and C2 equals that. So two typos in this thing. Yeah. So here, right, so here's what I said, but I said kind of quickly. Here, C1 and C2 are arbitrary convex sets. They're just whatever set you want. They are both convex. But here they are specific convex sets. I'll even go, well, I shouldn't say that they are convex sets. They're specific sets that may or may not be convex. I don't know. I mean, there's no final exam, so maybe on the midterm, but. What was that?
Was there a question the last one?
Was there a question?
Was the last one the 3-line thing? Is that a question?
Is this a convex set or not? Yeah, it's this little button here. It's just hard to. Okay, 25 votes, creeping up. We'll give it a little more time. I think there isn't quite. Like 50 was about the quorum we get, right? Modulo 50 people not being able to load the page. All right, so start getting in your final answers. Again, each one is a separate question in some sense, so if you don't get all of them, it's not like you get 0 or full credit or 0 credit. You will get partial credit for the ones you answer correctly. Don't worry. And it all counts for a fairly small part of your grade anyway, so as much as it, more as I said, the point is to just answer them. And answer them correctly. But try to get them right. Don't just, click random things. It's sort of against the spirit of the thing, right? All right. 4 more maybe outstanding votes, at least compared to last time. There may be some people still entering stuff. Okay, we'll go 10, 9, 8, 7. That was a really oddly timed bit there. Okay, I'm going to be done. There's one more person, at least last time there were 50 votes, but maybe a low. Oh, there were 53. Okay. All right, so closing in a few seconds now. Get your votes in. Am I there? 51? Okay. Closed. All right, let's look through them. Okay, so set x R2, x greater than 0, x is between -5 and 5. That is a convex set, right? Regions are convex sets, so intervals are convex sets. These are both intervals here, right? It's fine that one's open, still a convex set. You could also write this as a linear inequality, by the way. You could write this as terms in a matrix. So actually, I should point that out. Remember, where did I put my? There it is. Remember, we said that this thing is a convex set, right? You could write this like this. You could say that this is you have 0 or 1, 0, and then 0, 1, and 0, -1. This matrix times x is less than or equal to, this would be actually -1 here. Sorry. -1 here. This would say x less than 5. This would be less than or equal to 0, then 5. And then 5 again here, right? So that this can be represented as a set of linear inequalities, and you can do that for a lot of these cases. This one here, also a convex set. This is linear equalities, only difference. And that definitely is also a convex set. The same thing holds here if you have a linear equalities there, and you can represent it in the same way. This is a convex set. This is a circle around the origin, right? So this is this set here. That's the set of all points such that x1 squared plus x2 squared is less than or equal to 1. This the whole region here. That's this set. That is convex. It's a circle. This one is also correctly, most people got it correct. It's not convex, right? Because that would be the points that are equal to 1. Just the circumference of that circle, right? And it's apparent that if you have this point here and this point here, the line between them does not all lie on that circle. This one here is the intersection of the union of two convex sets, essentially, and most people got it right also. This is not a convex set. You can have two convex sets, perfectly convex sets, one here, one here. Their union is not convex, of course, because you can have a line, one point there, and the line between these two things is not convex. This, similarly, is another example of one of these. This region here in particular is a line that is this line here where you have 2 and -2, and you're on this side or that side. Not a convex set because you have points in the middle that are averages between those two. Finally, this one, people got it right too. It's kind of a tricky one. Even without the typo, it's kind of tricky. The idea here is that this set, in general, a union of convex sets is not convex. But here, one of the sets is a circle, and the other set is a box around this. So in fact, their union is just equal to the box, and so it's still a convex set. But I think most people got those correct. Again, if you didn't, there are some lecture notes online, and going back through the slides here and going on lecture notes online will hopefully help review some of that material. Okay. All right. Now let's at least start in the 5 minutes we have left. Convex functions, and I'm not going to. I probably will just define them, and then we'll stop there, and we could pick up next time with some examples. Where's my eraser? Here it is. I will define them, and then we can look at examples next time. All right, so a convex set we defined as you take a sort of a line segment between any two points in that set. It has to lie within that set. A convex section is kind of similar, but it's a little bit different. And it's important to kind of see the distinction here. So a function f. So f here is a function, importantly, from Rn to R. So it takes vectors as inputs and outputs real numbers. This function is convex if for any x and y in Rn, and again, theta in the same case, between 0 and 1, if f of this linear combination is less than or equal to the linear combination of the function values. Now what this is saying is, if we look at the function like this, we take the point, this is the point here x, this is the point here y, so this value here is f of x, this value here is f of y. If we take a linear combination of these 2 points, that would sweep out the function and evaluate it, the function at that point. That would sweep out this part here, right? That's evaluating the function at every point between those 2 points. Right? This quantity here is taking a direct average between those 2 output values. So what this quantity here does is it sweeps out the line that connects these 2 points. So that's, depending on theta, sweeping out that line here. For a convex function, all you have is that this line has to lie over the function itself. That's the definition of a convex function. Now, it is not always the easiest way to verify a function is convex or not. That can be very hard to actually verify for some functions directly. And we'll talk about another condition in a second on the next slide, but probably next class, that will actually be sometimes easier to check. But this is the definition of what a convex function is. And then the other one just follows from this one. So convex functions in some sense are kind of, they have to be always kind of upward curving, right? Because if they're not, if you have something like this, so imagine you have a function that can even still be increasing, but say you have a function that looks kind of like this. Okay, so it's always increasing, but you can find a point here and a point there where this line lies below the function. And you can't have that for a convex function. So convex functions are kind of always increasing kind of in a bowl shape. Intuitively, you should sort of think of them like that. If we say a function is concave, if it's the opposite of convex, it's negative f is a concave. So concave is the same thing, just in the opposite direction. Plenty of functions are neither convex or concave. It isn't one or the other. Those are both very specific classes of functions. And if it is both convex and concave, we call it affine. And in fact, affine functions have a very specific form. They have to be the form of the following. So if a function is convex and concave, that means the function, so you draw the function, right? That means that the line between 2 points has to lie both above and below the line. So the only possibility there is it has to lie on the line, exactly, right? So in fact, the only sort of allowable affine function is actually a line in some sense, right? You have to be, so that whole, this line connecting these 2 points here has to lie, greater than or equal to or less than or equal, and less than or equal to that function. So the function has to be the line itself. And in fact, for functions that are take vector inputs and return a scalar output, the only form you can have for an affine function is to say that f of x has to equal a transpose x plus b, little b. It has to be in that form. Remember, this is an inner product between some a here. A is also a vector in Rn now. B would be a real valued number. But this is the only form that is actually both convex and concave. What this means is that we'll see in a second, for those, say, equality constraints you mentioned before, when you have inequalities that are, you want to have equality constraints, but you can only have inequalities, your inequalities have to be both convex and concave. So you have to actually have the only allowable equality constraints in a convex program are in fact affine equality constraints. But we'll get to that later. Okay, so next time we'll pick up talking more about functions, and then also probably more exciting to everyone, we'll talk about how you actually go about solving these things.